All right. And plus, you guys know, think about basketball. Let's say it comes down to a free throw and you miss. You're not the reason the game was lost. Yes, you had the chance to win it, but it's lost when you missed that one rebound or you didn't, you threw that ball away or whatever. Like, there's other things throughout the game that affect it, but everyone always looks at the last play, so it's not just his fault. Anyways, moving on. I can't stand the Eagles, so that's unfortunate. All right, here we go. Now, 534. Look at the vapor pressure lowering. If a solute is non-volatile, that is, it does not have a measurable vapor pressure, meaning it doesn't evaporate very well. So, for example, sugar, salt, they're non-volatile. They don't just evaporate. Okay, but gasoline is volatile. It evaporates very easily. The vapor pressure of its solution is always less than that of the pure solvent. We talked about this last week. That's something I hope you understand. If you have water, it'll evaporate at a certain rate. If you put salt in that water, it'll evaporate much slower because you have forces of attraction in the water now, so the vapor pressure decreases. That's what that means. All right, so thus the relationship between solution vapor pressure and solvent vapor pressure depends on concentration of the solute in the solution. So if you have more salt, for example, it's going to affect the vapor pressure than just 1 grain. All right, if you have a lot of salt versus 1 grain. This relationship is expressed by Raoult's law. Write that in your notes. Raoult's law. We didn't do that yet, did we?
Yeah.
Oh, we did. Okay. Did we write P1 equals X1 times P1 naught? Okay, good. That's right. We did. That's okay. It's good to review. So that is the equation. We're going to do a practice problem here in a minute. Basically, what this is saying here is that P1, that's the vapor pressure above the solution. I say vapor pressure of the solution. It has to be above it. You can't measure vapor in a solution. So that's the vapor pressure above the solution. X1 is the mole fraction of the solution. And then P1 naught is the vapor pressure of the pure solvent. That P1 naught, that's going to be given to you every time. Those are in charts. That tells you the vapor pressure of water, for example, at 30 degrees. So just to give you the heads up of mole fraction. So mole fraction here. So again, if this is mole fraction of, let's say, of the solvent. So let's say it's water, of H2O, right? So let's say we have a beaker and we put NaCl. So we have a bunch of salt, Na plus Cl minus in here. So this is NaCl AQ. The way to calculate this, so if you don't know this, you need to write this down. You take the moles of H2O divided by the total moles. So that would be your moles of NaCl plus moles of H2O. So it's part over whole. That's how you get mole fraction. Essentially, it's the same concept of like percent composition, except there's no percent. You don't multiply it by 100. It's part over whole, and then you get a decimal, and that's going to be X, or mole fraction. The mole fraction cannot be 1. It's always less than 1. But I will say the mole fraction of the salt, so if we were to reverse this and do moles of salt over total moles, your mole fraction of water and your mole fraction of salt will always equal 1, which is like 100%. So for these problems, we only need moles of your solvent divided by total moles. So this is always the solvent moles on top. But I'm just kind of explaining the full concept that if you have the mole fraction of water and add it to the mole fraction of NaCl, that's always going to equal 1 because 1 basically is 100% of this solution. This is an important concept moving forward. Just to understand the mole fraction is made up of 2 parts. If you add them together, of course, it's going to equal 1. That should make sense. I hope it does. And again, 1 means 100%. So a certain percentage of solution is water, certain percent salt. Together, that's 100% of the solution. All right. Did I give you a problem already? Okay, all right, so now I just explained a little more. Go ahead, I'll give you a couple minutes. I don't know if I made that up or what. Nicole, can you read it to me, please? Oh, we're doing the one in the book. Okay. Oh, right there, the 218, that one? 218 grams of glucose? Okay. Right, so don't look at 535. That gives you the answer. So you're going to find the mole fraction of of water with the glucose, right? You have 460 milliliters of water, convert that to moles. You have 218 grams of glucose, they give you the molar mass of 180.2. So you find the moles of both, and the first step is to find the mole fraction. Then they give you, they tell you on page 199, I'll just look that up for everybody here. Page 199, the vapor pressure of water at 30 degrees is 31.82. Oh yeah, we already looked that up too. 31.82 millimeters of mercury. So you just multiply that by the mole fraction and call it a day. That's it. Then we'll do one more of these to make sure we're good. And then I'll give you some homework on this and we'll move on. Okay, the answer is 30.4 mmHg. If you looked at page 535, you already saw that anyway. But I'll just go through it with you anyway. So you have 218 grams of glucose times 1 mole over 180.2 grams. Grams cancel. So moles of glucose, we get 1.21. 1.21 moles. Oops, that one. How much water do we have?
460.
Or what?
60.
460 grams? which is grams, because the density of water is 1 gram per milliliter. Okay, so 460 grams times 1 mole over 18 grams. So moles of water, we get 25.5. So the partial, or the, it's a lot like partial pressure actually. We've done formula just like this with the gas laws. The partial pressure, partial vapor pressure, P1 of the solution would be 25.5 divided by 25.5 plus 1.21. All that times, what was that number? 31.82? 31.82 mmHg. And when you do that, you get 30. So this is 0.955, which makes sense. Most of this is water, right? So your mole fraction for water should be really high. 0.955, again, that makes sense. 30.4. 30.4 millimeters of mercury. So if they ask you what is the vapor pressure lowering, that means what's the difference? Well, if it's 31.82 millimeters of mercury as a pure solvent and 30.4 as a solution, you would subtract it, and that would be your vapor pressure lowering, which is 1.4. So about 1.4 is the drop in pressure when you dissolve this much glucose in this much water. So if you have this much glucose, dissolve it in this much water, the vapor pressure drops by 1.4 millimeters of mercury. Why? Because there's forces of attraction between the glucose and the water. Okay, so we're going to move on past that here to the next section here. Look at the bottom of 535. If both components of a solution are volatile, that means they evaporate very easily. Like if you mix acetone and gasoline together. Okay. The vapor pressure of solution is the sum of the individual partial pressures, so it still applies. So, for example, if A is acetone and B is gasoline and you mix them, you can do the same equation, you just do it twice, once for each solution, flip it for each part of the solution. And it says where PA and PB are partial pressures over the solution for A and B. So again, you do the same exact formula we just talked about, but individually, one for A and one for B. And then the total pressure above the solution would just be A plus B. So look up here for a second. So instead of P1, it would be PA and then PB. And then when you get these two numbers, you just add them together, and that's your total pressure. So if it's a non-volatile, you just do this once, and that's going to be your pressure. But if you have, instead of glucose, you have something that will evaporate very easily, you have to calculate this for both of them, and then add it together, and that's going to be your pressure above the solution. And again, they give an example here. Benzene and toluene are two volatile solutions. So don't keep reading. Let me ask you this question. So, picture time. All right, so draw a beaker. Okay, in here, all right, let's say we'll do this just for the sake of the drawing here. Let's say this is A and this is B. Assume they mix, but just to keep it straight so we can see here. All right, let's say this is benzene, and let's say this is chloroform. Is that the two they gave us there, right? No, toluene. Toluene. Okay, so let's say we have a mixture of those two. They're both volatile, meaning they both evaporate very quickly. Let me ask you this question. If A is more attracted to B, will the vapor pressure be higher or lower than expected? If A is really attracted, if these two are really attracted to each other, will the vapor pressure be lower or higher than we expect? Lower. Does that make sense to everybody? Why does it make sense? Paige, why does it make sense? Right, it's not, less of it will evaporate because it is too busy being a liquid, being attracted to each other. Good. What if A is more attracted to A and B is more attracted to B? Will they want to stay down here as a mixture? So what would happen to the vapor pressure? It would would be higher than expected. So when you do these calculations, in real life, if these are really attracted to each other, it's going to be lower numbers than expected. And if they are really attracted to themselves, it's going to be higher. So nothing new here. And again, the concept is probably more important to me than doing the calculations, just because then you can understand it, I hope. Now let me ask you this question. Which scenario is exothermic, which is endothermic? So I just gave you two scenarios. A and B really attracted to each other, or A attracted to itself, B attracted to itself. Which one is going to be an exothermic process? Which one's going to be endothermic? Ben, you seem to have a grip on this. What do you got?
If they're attracted to each other, it's exothermic.
Right. Just like you put salt and water. If they're really attracted to each other, the solution should get hot because it's going to be releasing energy. If these two are really attracted, that's a favorable process. And what I want you to start memorizing is favorable processes in chemistry release energy. So favorable meaning they want to mix, that's exothermic. If they're not attracted to each other and they want to evaporate, then that's going to be an endothermic process. It's probably going to get cold. So the only way it's going to force itself to mix is taking energy in and weakening those attractions for themselves. So I know I didn't write anything down there, but I think sometimes better just to discuss that. Plus it's more of the same. All right. Here's how the book explains that. Look at the bottom of 536. Don't worry about those graphs. Case 1, if the intermolecular forces between A and B are weaker than those between A and B molecules, so between A and B are weaker than between A and B, then there is a greater tendency for them to leave the solution, and then in the case of an ideal solution. So I said it backwards, I'm sorry. If A and A are more attracted to each other and B are more attracted to each other, then they will leave the solution. Consequently, vapor pressure is greater than the sum of the vapor pressures predicted. And then case 2, top of next page, if A and B molecules are more strongly attracted than their own kind, vapor pressure is less than the sum of the vapor pressures predicted. And then it says, thus, or that is, mixing is an exothermic process. So case 2 is exothermic because it's favorable. Case 1, not favorable. And at the end there it says it's endothermic. So if you can remember those general themes, that's important the rest of the year. If it's favorable, exothermic. Not favorable, endothermic. All right. I'm going to give you one practice problem here with this volatile liquid stuff, and then we're going to set up the lab. I hope we have time. We're getting close here. All right, write this down, please. We have a solution prepared by mixing 5.18 grams of acetone. So we have a solution, 5.81 grams of acetone. Again, that's a volatile liquid, and 11.9 grams of chloroform. Okay. At 35 degrees Celsius, acetone has a vapor pressure of 172 torr. At 35 degrees Celsius, chloroform has a vapor pressure of 147. And then it says, assume ideal behavior. Assume ideal behavior. By the way, the solution's at 35 degrees. That's why I gave you that information. Calculate the vapor pressure of each liquid. Calculate the vapor pressure of acetone and chloroform above the solution. So I'm going to do this one with you because you have one example in your notes of non-volatile. This is an example of volatile liquids. The non-volatile is way more common than this. But, so they give you the mass of each because you need mole fractions. You need to find moles. They give you the vapor pressure because that's your P1 naught. So essentially, you're solving for this, right? So you need the moles for that, and this here, that's what's given to you. That is the constant. So at 35, that's already been determined. So based on the moles, that changes this number. So part A, you're calculating this P for acetone and chloroform. So convert those to moles and solve for that. Go ahead and take a couple minutes, then I'll go over that part with you, and then we'll move on to the next part. Some more questions here. So solve for moles of acetone, moles of chloroform. Then you need to use this equation for each one. All right, sorry. Acetone, C3H6 0 0 O, and chloroform, HCCl3. You guys didn't know that? Let's go speed calculations here. We gotta at least help me get everything set up. We'll have to. Anybody want to volunteer and come in later and help me do that?
Extra credit?
No.
No.
Liz, any free time later? I know you do. Feel free to come in later and help me set those up.
I'll come in, what is it, 4th? Yeah, sure.
Oh, yeah,
What do we have?
I just need help connecting them to the Chromebooks. This is quicker than one person. Let's make sure everything works.
I was sitting in the lab watching the
Sounds awful.
What is it?
It's a movie on Einstein and like what led up to his discovery.
Physics?
Especially George. Oh, that's nice.
I heard a quote by Einstein recently. It said, "Life is like a bicycle. You have to keep moving to stay balanced." I like that quote. All right, we done?
No, oh my god, I don't even.
How many moles of acetone do we have? 0.1. How many moles of chloroform?
I don't know.
Didn't get there yet.
What's the molar mass of acetone? 58 grams. What's the molar mass of chloroform? Anybody?
Wait, did you get point one?
It's 0.1 moles of acetone, yeah. And chloroform. Both are 0.1. The molar mass of acetone is 58 grams. The molar mass of chloroform is 119. 119.35. So, I know I'm talking and going quick, but this is easy stuff. Everyone here can convert those to moles. You can't do that, then something's wrong. So, you have 0.1 moles of the acetone and 0.1 moles of chloroform. You don't need to do the mole calculator or the mole fraction. You could, but what's it going to be? Okay, how do we get the mole fraction of acetone? It's going to be 0.1 over 0.2, which is 0.5, right? Okay, thank you. So that's the mole fraction of acetone, and then the mole fraction of chloroform is exactly the same. So if you have equal amounts of both, then the mole fraction is going to be a half for both of them, because it's part over whole, and that's where 0.5. So mole fraction of acetone is 0.1 over 0.2, which is the total moles. Same thing for chloroform. Okay, so now the vapor pressure of each one you would do the partial pressure of acetone here, which is vapor pressure of acetone, it's the same thing, is going to be 0.5 times 172. So think of it this way. If you have just a beaker with acetone in it, that is your vapor pressure. But since you have chloroform in it, it's screwing up the vapor pressure a little bit. That's why we need to take this number into account. So 0.5 times that number is actually the vapor pressure of the mixture of the two. So that's going to be, whatever that is, half of that number, 86. And then you do the exact same calculation for chloroform. Partial pressure of chloroform is 0.5 times 147, which is 74. Now, let's say on an AP test, you did that. And now part B, this isn't the question I have, but let's say it said, okay, a student measured the vapor pressure of the acetone and chloroform above this solution. The vapor pressure in reality is actually 80, and the vapor pressure of the chloroform is actually 70 torr. Explain why. What would you say? Right, so you would say because the acetone and chloroform are strongly attracted to each other, that decreases the vapor pressure. And then they could ask the other one. They could say, well, the actual vapor pressure is 90, and the actual vapor pressure is 80. You would say acetone and chloroform are not very attracted to each other, so they evaporate very easily. That's where the AP is going to get you. Maybe you can do the calculation if they give you the numbers, you can figure that out, but then they ask like the why question. That's the part I care about the most as far as doing well on the test and understanding what you're learning. Okay, now, part B. Here's a question. Calculate the total vapor pressure of the solution. So, you have inside the beaker here. Okay, so let's do it this way. We have our acetone over here, chloroform over here. It evaporates, assuming they're mixed, but this is just easier to visualize. This one's vapor pressure is 86. This one is 74. So what's the total vapor pressure up here? That's what part B is asking. Calculate the total vapor pressure. Logically, sitting here right now, hopefully some of you are coming to this conclusion. If I know the vapor pressure of this one, and I know the vapor pressure of this one, what's the total vapor pressure? Just add it. That's it. So part B, calculate total vapor pressure above solution. It's going to be 86 plus 74. What did we say that is? 160?
Yeah.
160. Hopefully that makes sense. I don't need to get into a lot of detailed explanation there. If you only have two substances evaporating, then the total is going to be both of them added together. That should make sense. That was, if you look on page, if you still have your book open, page 536 on top, that's what they explain. The individual pressures added together equal the total pressure. That's Dalton's law. Learned that a long time ago. Okay, part C. Calculate the mole fraction calculate the mole fraction of acetone and the mole fraction of chloroform above the solution. Alright, so now this is where it gets a little squirrely. Write that down. Part C. Calculate mole fraction above the solution for acetone and chloroform. Above the solution is the key. You just calculated 0.5 and 0.5 in here. So the mole fraction of acetone is 0.5 here and 0.5 here for chloroform. That's in the solution. The question wants to know what's the mole fraction up top when it's a vapor. Now, when liquids evaporate, they turn to vapor. What do vapors act like? What other phase? Gases! What's the only equation we've learned with moles in it for gases? The only one that matters. So if I give you moles and temperature and volume, can you figure out the pressure of a gas? Yes, you can. What is the equation? Perfect. PV equals nRT. Yes. So, that's the key here to this question. So now you know the pressures of each one of these. You know the temperature. You know the gas constant. What about the volume? Did I give you a volume? Didn't. But that's irrelevant. Yeah, that's irrelevant.
You're just not using
Okay, look up here. Is the gas constant? Look up here. Is the gas constant the same for both of these vapors? Yes. So that doesn't matter. Is the temperature the same? Yes. So that doesn't matter. The volume of this is the same for both because they're both in the same solution. So the volume is also constant. So the moles is equal to the pressure. So when you use the PV equals nRT for this type of question, and they want to know mole fraction up here, you don't need the actual moles, you can just use their vapor pressure. So for these types of problems, I know this is probably a little confusing, but for these problems, you can use the pressures, which we just calculated, as the mole fraction. So the mole fraction for acetone above the solution is the vapor pressure of the acetone, which is 86, divided by, what did we say it was? Wait a second. Yeah, 160. Yep, 160. And then the mole fraction for chloroform is 74 over 160. So what I'm trying to make a connection to here is the gas laws and vapor pressure are connected because vapor acts just like a gas. So the only thing that I left out in this question that would be make more sense to you is the volume of these would be the same. So I told you it's irrelevant, but they would probably give you the volume of each one so that you knew the volumes were equal. So if all these numbers are equal, only pressure matters. So the mole fraction of acetone above the solution is, what'd you guys get? Someone do that quick, because my number is different. I got fraction or decimals. Real quick, what is this? 86 divided by 160.
0.5375.
0.536. What about this one?
0.4625.
0.462. Okay. All right. So I will text the homework later. Tomorrow, the plan is to do the lab, but it's looking bleak. So I may just show you how to do it, and then we'll take notes on kinetics. Who's missing Wednesday? Is somebody missing Wednesday? No?